Today we're going to be looking at a technique that scientists and forensic scientists use to solve crimes and also to determine paternity with DNA technology. So this technique is called gel electrophoresis, so DNA gel electrophoresis. So what scientists do is they actually collect DNA from the crime scene, and they'll also collect it from two potential parents and run the DNA through a gel, which we're going to be talking in more depth about, to see what markers the DNA has in common. So for example, looking down here at the bottom right, we have the DNA that was collected from the crime scene, and then we have the four suspects and the DNA from the four suspects. You can see the bands, and what you're going to be looking for when you look at the DNA gel electrophoresis is which bands match the bands from the crime scene, or which bands match the potential parents of that child. So for the crime scene bands here, we can see that suspect 3 also has DNA fragments that are the same length, thus making bands that are the same. And we're going to get into that more in a second. When you're looking to read a DNA gel, like we just said, you're going to be wanting to look for the bands that match up to a suspect. So the sample DNA from the crime scene is here. You see that the DNA bands that are smaller in size have moved farther in the gel, and the DNA bands that match the ones from the crime scene with 33 base pairs, 19 base pairs long, and 19 base pairs long, those are the bands coming from suspect B. So most likely, suspect B was responsible for committing the crime. When you're determining the paternity, you're going to be looking for the child's bands to be coming from both the mom and the dad. So for example here, and BP stands for base pairs, so how many nucleotide base pairs that strip of DNA is. So Juliet here is the mom. We have the child here. You can see that the child has one fragment of DNA that's coming from the mom that's 100 base pairs long. And we're trying to determine the paternity. So we're trying to determine if Alex here is the father or if Hugo's the father. So if you're looking at their bands of DNA, you want to find a band that matches up with that child's band. So the child here has one band in common with the mom and one band in common with Alex. Since Hugo also has the band in common with the child that Juliet has, it's unlikely that he's the father because we see the child is also getting a band from somewhere else, presumably from Alex, who also shares that DNA band. So now let's take a look more closely at how gel electrophoresis actually works. So DNA profiling includes a whole bunch of different techniques, karyotyping, which we're going to talk about, and also gel electrophoresis. So what happens is the DNA is collected from the crime scene, then it's cut into fragments using restriction enzymes. So restriction enzymes, they come in, just like we talked about in genetic engineering, and they chop the DNA at certain places. What happens next is that the DNA is run through a gel. So it's actually very similar to Jell-O. The gel electrophoresis then separates the DNA bands based on size. So DNA has a negative charge. So when you put it into the gel at this end, it's going to want to migrate to the positive side, or the anoid. So once the DNA goes into the gel, the shorter, smaller pieces of DNA are going to be able to migrate farther. So they're going to be able to move farther in the gel because they're tiny. Think about if you're a small person, you're going to be able to run more quickly through a tub of Jell-O than if you're a really big person. The DNA fragments that are longer or larger are not going to be able to migrate as far. So if you're looking at the DNA gel, the longer molecules and fragments are closer to where they started, up here at the negative side, and the shorter molecules are farther down. So the first step when performing a gel electrophoresis is to isolate the DNA from the crime scene. So this involves taking fragments of hair, taking blood, taking a tooth, taking saliva, and taking the DNA out of these segments that you collected from the crime scene. The second thing you need to do is to amplify the DNA. So let's say you only have one tiny slab of saliva. That might not be enough DNA to actually run the gel electrophoresis. So scientists use a technique called PCR. So PCR uses heat and DNA polymerase to actually enable the DNA to rapidly replicate and divide. So you're taking the DNA fragment that you have and you're making multiple copies of it, hundreds and hundreds of copies. The next thing that you're going to do is you're going to compare that DNA using the gel electrophoresis. In this picture here, you can see the gel and the pipette that's being used to pipette the dyed gel into the dyed DNA into the gel. So for an overview of gel electrophoresis, what you're going to do is you're going to take the DNA fragments of different sizes, place them into the gel on the negative end. Since DNA is negatively charged, it is naturally going to want to move, once you turn the power on, towards the positive end. The strips of DNA that are longer are not going to be able to move as far, so they're going to be stuck closer to the beginning of the negative side. The DNA strands that are shorter and faster molecules are going to be able to move farther in the gel and will be at the opposite side, closer to the positive anode. Once you've run through the gel, you'll be able to see that the completed gel, you'll have certain bands. So bands are referring to collections of DNA that are one particular length. So you can see a band here, a band here, a band here. So it's showing how long that DNA segment is. So like we said, you're going to use restriction enzymes to cut the DNA into fragments. So similar to when we talked about genetic engineering, those restriction enzymes are going to come in and splice the DNA at particular points. So this restriction enzyme here is only cutting in between the sequence GC-GC. So if it sees GC-GC, it's going to make a cut. GC-GC, it's going to make a cut. Another cut here, and another cut here. Once we have that cut DNA, from suspect 1, it was 17 base pairs long. Suspect 2 had 8 base pairs long in between the restriction enzyme and 12 base pairs long. You're going to take the DNA, place it into the gel electrophoresis machine. As you can see, the longer base pair, 17 base pair fragment, is not going to move as far in the DNA gel. The shorter base pair fragments from suspect 2 are going to be moving significantly farther towards that positive side of the gel. Once you take the gel and you put it into the gel electrophoresis machine, you have your mixture of the DNA up here. The longer fragments are going to move more slowly towards the positive pole, and the shorter fragments are going to move faster. The bands is what we will be looking for when we're determining paternity or whether or not a suspect is guilty. And looking at the bands, those are the fragments that are exactly the same length. Here's just another diagram to show how the longer fragments are not going to be able to move as far through the gel as the shorter fragments that will be able to move much farther and create that DNA band that's